Hi, and welcome back to MSc. In today's video, we're going to be looking at Le Chatelier's principle, specifically how changes in concentration affect the position of the equilibrium. So here we have an equilibrium reaction, and it's completely generic. We have 1 mole of substance A reacting with 3 moles of substance B, and this is in equilibrium with the products of 1 mole of substance C and 2 moles of substance D. And as was previously discussed in an earlier video, we can think about an equilibrium being a balance of those same forward and reverse rates of reaction, not equal amounts. And so let's assume that this equilibria lies to the right. And so it's always as it's written, and we're going to say it lies to the right, meaning that there are more products present at equilibrium when we have that forward and reverse reactions being equal rates than we do of the products originally. I'll place the arrow right about there for argument's sake for now. And so what Le Chatelier's principle states is that whatever we change about this, it's going to try to undo the change. I also have for reference down here in the bottom, I have our equilibrium constant expression, which is the products raised to their coefficient exponents and over the reactants raised to the exponents that are the coefficients as well. So we understand it's going to try to undo whatever change that we do to the reaction. So let's assume that we are going to increase A. I'm going to add more of A and see what that does. So we're going to add more of this. And we have to remember that in the Kc value, the values that go in for the concentrations are the equilibrium values. So an equilibrium is established, and then I add a little bit more of substance A. And so Le Chatelier's principle says that the equilibrium will shift in such a way as to try to negate the change I did, try to undo what I just did. Well, I just added A, so it's going to try to undo that. And by doing that, it's going to try to shift and create even more products, consuming some of B in the process, but also some of the addition of A that I added in. So what does this do to our equilibrium position? Well, it shifts it further to the right. It's going to bring it over, and I'm going to actually create more product as a result than I would have had originally. The other piece we're going to consider here is what happens to Kc, what happens to my equilibrium constant. Well, what's really interesting here is that Kc remains unchanged. And as we go through these videos, we're going to see that only one thing changes Kc, and that's temperature. It's temperature dependent. So what I'm saying is, when we establish this new equilibrium position, Kc will be unchanged. And that might seem really bizarre, and how can that be true? So let's look at this from this equation perspective. And let's say, okay, well, I have now I'm going to have more of these in my new equilibrium position. Those both will increase, right? Because I've added more of A, the reaction will move over further to the right, creating more of C and D. So right now it looks like, oh, Kc is probably going to get bigger. Additionally, I'm also going to have B get a little bit lower. And I know B is going to get a little bit lower because I'm going to consume some of it in addition to the A to create more of this, of the C and D. The A value, though, the A value has increased because I added some in. And while I decrease it a bit by using some, I'm trying to undo that addition. I don't fully undo everything that I've established by the addition. So what this means is this new ratio that's set up with these different concentrations, predictably these will be larger and the B will be smaller. All of that would lead to a bigger Kc. However, the A concentration will be larger than it was originally in the original equilibrium. And this new equilibrium will be established in such a way that Kc is not changed. Right? So this here is unchanged. And that's really interesting And it's, again, a little bit hard to imagine that that's true. But we have to imagine that that's what's going to happen with these concentrations. And you have to trust that that's going to work. And there is a new value of C and D and B and A such that Kc will be the same value. And that's what happens. So an addition of an added substance does not change Kc. So let's now look, for example, and see what would happen if I added some of substance C. Well, that would mean that this equilibrium would now shift back away from that, trying to use it up. So it would shift to the left. Now, how far to the left would depend on how much C I added. So it would shift to the left. Let's say it's still favoring the products overall. And what that would mean is I could picture that, well, that's going to decrease my value of D, and it's going to increase my value of A and B. And so you might look at that and be like, oh, well, that means that Kc is going to be smaller. But again, you have to remember that we added some of C, so this will actually be larger than it originally was. And this new equilibrium was established with these new values, again, such that Kc is unchanged. Right? So again, it did use up some of the C that was added, substance C. A new equilibrium was established such that Kc is not changed. As a final example, let's look at what would happen now if some of this was removed. So I'm going to remove some of substance D. And this is more common than maybe you would think. In an industrial process, it's advantageous to remove some of the product, especially if it's a product I'm interested in harvesting. So let's remove some of substance D, so it goes down heavily. And what that would mean then is that my equilibrium would shift over to the product side even more. It would shift to the right. As a result, that means that some of substance C would be produced. The concentrations of B and A would go down as they are being consumed to make more of substance D. We're trying to replace what was removed. It's not going to fully replace what would be removed. And so as a result, we were still going to have a D value here that's lower than what we originally had in our equilibrium. And again, a new equilibrium is established such that Kc is unchanged. So we can see now that when we change concentration by either adding or removing, the equilibrium will shift. If I add a substance, the equilibrium will shift away from that side of the equilibrium. And if I remove stuff, it's going to shift more towards that side. Again, remember, it's really important. An established equilibrium just means forward and reverse rates are equal. And again, it's really cool here. Kc does not change. It stays completely the same with changes in concentration. I hope you found this video helpful. Thank you so much for watching. And as always, thank you for listening.